Hi, my name is Paolo Fracas. I am the founder of GenOPT. This video will introduce a microgrid simulator tool to optimize operation, design and location of multi-microgrids. Global warming and increase of energy demand are dramatic challenges. Microgrid is the technology choice to generate and deliver high quality of clean and cheap energy. They are small energy systems that enable us to integrate intermittent thermal and electric renewable sources with energy storages, generator, loads and utility grids. They incorporate generation, transmission and distribution of energy as a whole. Microgrids are capable of autonomous control to achieve power balance and optimal energy allocation over a given area in islanded mode or interconnected with other microgrids. During the feasibility design phase, policymakers, engineers need to consider several challenging financial, technical targets and constraints. The large amount of inputs to be considered have a great impact in the overall configurations, location and operation of the microgrid. Here is an example for the fuel cells, and then another for thermal collectors with heat pumps in our tool. To search the best fit among a larger number of configurations, I developed a suite of algorithms that simulate the techno-economic problem leading the objective inputs. The model computes each time step stochastic climate equations to predict energy available from renewables, calculate cost and energy flows of each distributed energy resources, thermal and electric stochastic loads, and then returns the fitness value of each configuration trial. Parallel evolutionary optimization and machine learning techniques are used to solve the multi-objective stochastic problem. The optimization tool solves a technico-economic model that simulates multiple microgrids. The model considers inner and outer thermal electric energy exchanged among distributed energy resources, interconnected microgrids, and utility grids. Different types of thermal and electric generators, energy storage are considered. Here are schematically represented with boxes named HMG. Different technical economic models based on analytical, regression, deep neural networks can be selected according to the desired resolution of the optimal outputs. The optimization computing algorithms combine sequential least square programming with a novel self-adaptive genetic algorithm. The SLSQP minimizes a loss-profit objective function with constraints to balance electricity and thermal energy flows each time step. At the upper level, the evolutionary algorithm mimics genetic mutation of a population of individuals. Each individual represents a configuration trial. The chromosomes of the parents are the distributed energy object forming the trial solution. Each generation, the genetic algorithm selects the best individual to minimize the stochastic multi-objective function until the global minimum is found. An innovative approach based on centroid cluster is adopted to manage fitness convergence and phenotype diversity. This method permits to improve the quality of results and quickly converge where the global minimum is located. With this graphical user interface, we can set up all the parameters to run our simulation. In this first page, we can start to set up general information like the name of the project, the start of the project, the duration of installations, currency, discount rate, and the main locations where to start our search. When we save all the data, we upload all the climate data sets that will be utilized to predict the energy from renewables. Here we can set up the grid scanning area, and then finally the other main parameters to run the simulation, like the resolution to speed up the computing time. In the next session, we start to configure the parameters related to the distributed generator, starting from the interconnection system, electric and thermal. We start the power, size, and bandwidth, the cost, unit cost, and losses, and the price policies related to the exchange of energy among the microgrids. In the next page, we can set up the load profile, starting with a minimum and maximum daily load consumption, and then we can, in this section, set up the profile for the energy demand services. In this area, we can put the price for sell energy to users, energy demand response service to the main grid, and other products that can be produced with fuel cell hydrogen generation in our microgrid. Then we moved to set up the renewables. Again, for solar and wind turbine, in addition to the size and the unit cost, we have to set up the profile to build the characteristic curves. Same for the lithium-ion energy storage. We have, in addition to set up the charging discharging rate, the state of health parameters. For the inverters, similar information, and then we move to distributed generator. We can set up a type of fuel cells if we produced as a byproduct water and heating, and the type of electrolyzer with associated tank for the fuels and for the heating water. For the traditional generators, we can set up different type of generators and the fuels. And then we moved to the grid, where we can set up here the hourly cost of energy that is sold and sell back to the grid. If there are grid outage, we can set up here, in addition to the size of the grid to consider. Then we moved to set up a thermal distributed energy source, starting from the electric boilers, with information regarding the size and the cost and its associated tanks. We can do also for thermal solar collector here with the tank and associated heat pump. If just only the heat pump operates in standalone mode, we can put here information. Same data can be added for the microgrid B. And finally, we moved to define our objective for the optimizations. We save the parameters, and then we can launch two different types of optimization. If we want to identify the best design, the best location, we click here. Otherwise, if we want for a specific configuration to identify the best operations, we can click here. And results are printed here for the two microgrids. In addition, we can show multiple variables with a plot in this page. Boxplot techniques are used to plot the quality and robustness of the results. This example shows distribution of best solutions in Bremen. Results are also returned in Excel. Here is an example of comparison between solutions obtained with deep neural network and analytical model. Sensitivity analysis can be executed. This is an example that represents the results associated to different hydrogen fuel costs. Key financial ratios of solutions are evaluated with bar plots. This work started in 2014 as a techno-economic task of the EU-funded research project PAN-Beyond, and then it continued at Bremen University in Germany as my PhD fields of research. Thank you for the attention.